Hey, this is Steven from RC Engineering, and welcome back to my development series. So this week we are continuing on with what we were doing last weekend, which was we were looking at the what are they called? The tiny Whoovs, or tiny Whoover, and looking at how we could better design one to kind of maximize how the engineering will go. And so this one we're going to look more into the materials and then kind of the concepts behind the material choice, more so than the actual design, because I think that the design is pretty good as far as how they're doing it for the most part. It's just kind of or how those designs that you saw in the first part of the series were. I think those designs are good. It's just material selection, fine-tuning on Betaflight, and now I guess we have Butterflight, but basically the difference between those right now that I know of is that they have different filters, which we don't really care about the PIDs because we're not adjusting with any sort of acceleration against us besides gravity, but we're on the ground, so it's not that big of a deal to have the PIDs because we're not going to be able to do backflips and stuff. So yeah, so we're going to be going over a few different things. I'm still, again, sick a little bit, so I might cough to clear my throat every once in a while. Because of that, I'm going to try to make this as short and sweet as possible. Obviously, that's probably not going to happen, but we'll give it a shot. So, number one is, what material will the hovercraft be made out of? That's number one. And number two is kind of whether we should have a skirt or should not have a skirt. And the first thing we're going to do is we're going to build it without a skirt. So now that we've answered that for the first part, obviously in the first section I showed that having a skirt is more beneficial for going over varied terrain. But in this case we're going to be doing this downstairs, nice flat surface, no carpet, no nothing. It's really, really nice to glide on. So then we have the second thing is, if we have, for example, motor stop taken off and we want to slide to a stop, what material will we put on the bottom to have what we call low friction? So we could actually have a controlled deceleration slide instead of like a just it stops just in a few seconds. So you could have like a controlled deceleration, a nice linear deceleration instead of an abrupt stop. So what materials can we go about doing that are low friction? And I will show how it's more than just material selection. So these two options of the material selection for number one, what the entire body is made out of, and then two, what the bottom surface for like a skid plate is. So as you saw from from Flight Test, which I need to do another video on backing their new endeavor with the what is it called? The golf course. Future of Flight or something like that. I'll have to do a video on that because I really think if you guys need to back it, and I need to back it as well. It's just getting kind of out of it. Anyways, okay. So what you'll see here is it actually does have a little slick surface on the bottom so that you could slide. And now let's look at what that surface is. They're using it sort of as a skirt, but as you can see, there's no cuts here, so it's not really a skirt. I think that's the drift bumper. Anyways, So you see that one of our first material selections is an option of having what this is. And I don't know if you guys are familiar with the foam board. So this is like Dollar Tree foam board, but this is a special version. The brown version is water resistant foam board. So basically what foam board is it's a layer of foam sandwiched between two pieces of basically construction paper. Now the water resistant version will have water get on top, and on when the water gets on the paper will not absorb it and let go. And then if they did, which is the white version that you get at most of, for example, Elmer's or even the Dollar Tree foam board at Dollar Tree stores where you get it for $1. What will happen is when you get water on that, the paper will just start to come off. It'll saturate the paper, and then the glue can no longer hold on to the saturated paper, and it'll just peel off. So that's what the difference between this foam board is. But what the construction paper does is that the foam board is very soft. So when you hit it with your finger or your fingernail or whatever, you'll permanently dent it. So what the construction paper does is it adds toughness to the top surface, so that if you hit it with something, it won't permanently deform, because the construction paper is giving it a little bit of toughness there on the surface. Yet it doesn't really add much weight, but you have to also think that it's using construction paper as well as glue to hold it on there. But that's assuming that when you peel the paper off, the glue comes with it as well, which that doesn't always happen. So that's basically what this is, and the reason why they're doing that is it's very easy to laser cut. Now, if you're not familiar, besides construction paper, foam board is made out of what's called XPS, or expanded polystyrene. One second. So expanded polystyrene is a version of polystyrene. There's two versions. There's expanded polystyrene and extruded polystyrene. And extruded polystyrene is the X, and the expanded is the E. So EPS is expanded polystyrene, and that's what you would see on most RC planes, or basically generally it's toy RC planes, little foam toy RC planes. That's expanded polystyrene, which basically means that you take the beads and you use a lot of pressure and heat. You inject them into a mold, and then with the heat, the cells will expand inside the mold to take the shape. While extruded polystyrene is where you have a die, for example, like a rectangle for like this. This is board, right? This is long, wide board. And then you push the beads, the polystyrene beads, through, and then you let it kind of expand to shape, and it comes out like expanded to its shape. So basically you push it into a tunnel, and then it expands into the tunnel. So let's say the tunnel is about 3 feet long or whatever, and then as it gets to the end of the tunnel, it cools and gets to its final shape, and then it will shrink, and they compensate for the shrinkage to make sure it always ends up to be the right size. So when it comes out of the machine, it's to the right size and the right specifications, and it's ready to go. And also, of course, they lay the paper on it at a later point. They add the glue and then add the paper. So those are the differences between the two. Obviously, extruded polystyrene you can make way extruded polystyrene you can make way faster than expanded, because expanded you need to push it into a mold, expand it, open the mold, and then take the part out. While extruded is continuous. It just keeps coming out of the die forever. As long as you're filling in polystyrene at one end and you're pushing it through, it'll keep going forever, and then you have a chopper that will chop its size. So polystyrene is very easy to laser cut, so that is why Flight Test uses it for a lot of their stuff. It's very easy to manufacture, and it's very easy to change your design. All you have to do is change your file and then cut it. You don't have to because it's extruded polystyrene. You also don't have to cut it. You don't have to cut additional changes in your mold. So let's look at some of the densities of that kind of foam board. So we're going to look at mainly this one here. It doesn't talk about Dollar Tree foam board, but anyways, it will Adams brand. Adams is Dollar Tree foam board, actually. So here we're looking at weight per square inch is 0.20 grams per square inch. So what we have is we're going to use that number to compare versus other stuff. Another option is if you 3D print it, you go on Thingiverse and you want to 3D print it. So what is the weight of so basically what we're going to be looking at is weight, because obviously we want to minimize weight, but yet we don't want it to break when it hits something. So how is its weight compared to its strength, right? And those are very crucial. And then we'll go over how those kind of backfeed into each other. So another one is if you're 3D printing and you're using something called polylactic acid. Polylactic acid is also known as PLA, PLA 3D printing material. And those have an average of 1.25 grams per cubic centimeter. And obviously that's not foam, it's a thermoplastic, while the foam is also a the foam is also a thermoplastic, but actually it might be thermoset. Extruded polystyrene. Let me see. It's thermoplastic. Okay, so it says depending on the type of polystyrene, it could be classified as a thermoplastic or a thermoset. So anyways, let's go ahead and look at the conversion to compare those apples to apples. So here is grams per square inch to grams per but how thick is it? 3/16 per cubic centimeter. Okay, well, 1 grams per cubic centimeter. So we're gonna have to my backpack in here. My backpack is not in here. So we're gonna have to do it in our head here. Okay, so we're gonna go from inches to centimeters, and use this piece of paper here. So 20 is 50.8, 30 76.2. 3 divided by 16, 0.47625. So 0.47625 multiplied by 50.8 multiplied by 76.2. There you go. 1,843 cubic centimeters, and then we're looking at grams. It's density. Density is weight over volume, or mass over volume, I guess you could say. So that divided by 115 divided by 1,843. 115 divided by 1,843 equals to 0.06 this is in centimeters, right? Cubic centimeters. Yep. So you can see the difference here. We have 0.0624 versus 1.25. So let's do this here. 1.25 divided by 0.0624. So PLA is about 20 times heavier than the foam board. Another thing is that PLA is very brittle. So I actually have a frame over here. I'll have to upload a video of my roommate Roger's frame here that he designed. He's new into designing. Designed the frame in PLA. First time out, hits the wall, and when he hits the wall, it just breaks one of the sides off of the side of the frame. Reason being is that PLA is very brittle. It does not, which means it does not flex very much before it completely breaks. So you have other materials that we're going to go over that are extremely flexible. So yeah. So obviously I think that in this case PLA is definitely not a good way to go. It is very friendly, earth friendly, or green, I guess you could say. But then foam board, but foam board is definitely the engineering pick here. So what else do we have? We have another thermoplastic that's slightly better in density than PLA, and you see it's 115 versus 125. But the reason why I wanted to bring this up, obviously this is not going to beat nylon, not nylon. Nylon's not going to beat foam as far as the weight is concerned, but the idea is that nylon is incredible material, especially for 3D printer filament. So nylon has a advantage of being extremely durable, or extremely tough they call it, which means it takes a lot of force to flex it, to get it to deflect, but even then you have to get it to flex really far before it will even break. Tallman makes some engineering 3D printing materials. Some of them are rated, a lot of them, pretty much all of them, are nylons, and even their lowest one I think is rated for like 200% flexing before breaking. Basically what that means is that you have to flex the material. You have to basically pull or elongate the material 2 times its original length before it will break, while PLA is about 4%. So all it has to do is stretch 4% its original length before it breaks, while the nylon is 200%. So it's 2 times its original length. So if it's 2 inches, it has to pull to 4 inches before it will break, while PLA will have to pull to 2.08 inches before it breaks, right? So that is the benefit of nylon. EPS is very brittle as well. So generally when you have flight test stuff, they will hit the ground, or any sort of foam board, when it hits the ground or hits a wall or whatever, if it's heavy, it'll instantly just snap a wing off. However, this is where the engineering comes into play. So again, if you remember from some of my other videos, F force equals MA. Oops, that's a really bad M. Right? And again, A is the acceleration, so how fast is your velocity changing, and M is mass, which is equal to force, which is either in newtons or pounds. Now, force, F, is what destroys materials, right? Is basically kind of the work that you're putting on a material to get it to bend. So for example, if I put, let's say if I have a piece of PLA or aluminum or whatever in between my fingers, and I begin to flex it enough, if it's thin enough, it will move. And basically what I'm doing is I'm applying a force in the center that's causing it to bend. So you want to minimize the force that you put on a material. So even if you have a ductile material, if you minimize the force that you put on it, you could actually keep it from destroying itself. So in this case, we don't really have to worry about you bending the hovercraft. We have to worry about when you hit the hovercraft into the wall, if it's going to break itself, right? So what you have is you have something called impact analysis or event analysis, where you have your hovercraft and you ram it into a wall. What is we want to minimize the force that hits that material. So there's two ways of doing that. Number one, materials. Well, actually, they're both. Well, material selection and design, but mainly material selection, right? Because if you have the same design for both, the material selection is what's going to make the difference. But you can design around the material and get similar performance out of both. So you have two options to minimize force. You can either drop down the mass or drop down the acceleration. Now, if we're racing, the acceleration is going to be the exact same. So this is not going to work. So the only thing that we could do is drop down the mass. And so obviously, if the mass of PLA for the same exact design is 20 times more than the extruded polystyrene of the foam board, that means that the same hit, we will add a whole lot less force, 20 times less force. So that means that we could hit the wall. Let's say that they both took the same amount of deflection, the same amount of warping before they broke. And I'm kind of jumping steps here, but you could say that you could hit the wall 20 times faster. It's not exactly true, because when you hit the wall, if you have enough force, you will deform the material. The material will deform, might not break, but it might, basically distort and no longer be the same. So if we pick the right material, we won't have to worry about that. So these foams are a really good deal. So what's another foam that we could look at? Now this is a foam that I really like. And I'll have to talk to you guys more about it, but this is another website. It's called RC Foam. I don't know if they're really stocking much stuff anymore, but anyways. Another one is called EPP, or Expanded Polypropylene, which this stuff is absolutely amazing. Low density and versus expanded polystyrene, and also something else that you're probably familiar with in models called EPO, which is it's got a really weird name. Can't remember what the O stands for. You guys could look it up, but it's another plastic type. EPO is very brittle compared to EPP. EPP is incredibly durable. So what it will do is it will just flex and then pop back to shape. So you could even make like a basketball out of this stuff, and it will bounce, right? Or a bouncy ball. It won't bounce very well, but it will bounce. Now if you did that out of EPO, it's not going to bounce too much. It's going to hit the ground and then come back. So EPP is incredible material. And Depron's a version of expanded polystyrene. Again, expanded polystyrene is still very brittle compared to EPP. EPP is a wonderful foam. Now, it does have one problem, and that is that it rips really easily. So it's called shear, right? If you put the material and you put your hands really close together, it'll tear really easily. So let's look at that. We're looking at density. It's not, oh, here we go. Calculate density from 10 piece ounce cubic feet. So grams per cubic centimeter was ounce per cubic foot to grams per cubic centimeter. So it says 20.8. Grams per cubic centimeter is 0.02 for the 1.3, and this is density. So actually, density. I think this was the density. Actually, it does tell you the density. So it's 1.3 pound. I think that's pound per foot, cubic foot, something like that, 1.3 pounds per cubic foot. Can't remember what the pound sign is, but we just figured it out. So this number right here, 0.0208. So not only is this thing, like, obviously it's 3 times less dense than extruded polystyrene. It's 3 times less dense. It's also, I'm gonna say, maybe 10 times more tough, ductile. So you don't even have to have a piece of paper on top. If you press into EPP, it will pop back, immediately rebound to its shape. If you hit a wall, it won't damage your wall or anything that you run into. It's just gonna bounce off the wall because it has, again, extremely good ductility. So it will just kind of, it won't even like transfer like the energy. Well, it will effectively transfer the energy. It won't just keep the energy in one spot. What it will do is you hit it. So for example, if you have a ball and you hit it in the front, basically you'll have like waves of the energy go through, hit the backside of the material, and then just like come back and then put a force on the wall, and then that will cause this ball to go backwards. So that's how a bouncy ball works, right? It transfers the energy to the back and then transfers it back to the front and then bounces, right? So on a harder material that's not as ductile, it loses a lot of its energy in here before it could hit the back and come back. On a ductile material, it doesn't lose very much energy. So on a bouncy ball, when you drop it and it hits the ground, comes back up, it almost comes back up from where you dropped it. So you didn't lose too much energy in here as far as the atoms bouncing off each other and creating heat, losing that height potential energy as heat. So expanded polypropylene is an incredible material, and I plan on using it a lot on my channel because it really needs to be brought to the forefront. But the problem is it's not as easily accessible as foam board. Alright, so now let's get into the next part, which will be very quick. So obviously the way, in summary, it's a lot better idea to use foam than it is to 3D print. Alright, so on to the next portion. How can we kind of get a lower friction surface? We'll go into one main material, but maybe we'll look at a few. So Alright, so let's talk a little bit about friction. So I'm planning on doing a entire what is it called? Rule of thumb on friction, rolling friction, and also regular kinetic friction or static friction. But basically what those are, and it's kind of an interesting equation. So this is kind of where our material selection also, not just for the bottom little skid plate, but also the whole entire piece itself, really comes into play. So here is a article from Engineering Toolbox. Let me put this over there. Put this back. So the equation for friction is force equals the coefficient of friction versus the normal force. Now normal force is basically the counteraction force of how hard the surface that you're laying on, the flat surface, is pushing back on the material that you're putting on the surface. But that is also equivalent, Newton's second law, I think. If you push on something and both of you do not move, the material that you're pushing on is also pushing back at you at the same exact force but opposite direction. So the normal force is basically the weight of the material but opposite direction. So, and also the the force of friction is basically a force opposite of your applied force. It's trying to keep your applied force from moving. So one of the ways of lowering friction is by lowering the weight of the material as well. So that is another thing that you could do here by picking the 20 times lighter and then the 3 times lighter for EPP. EPP. So now you have 3 times less friction. So this is 20 times less friction than PLA, and this is 3 times less friction. That is, of course, assuming that they all have the same coefficient. So let's look at some static coefficient, static friction. So it's not this is not kinetic friction, but static friction. Static is basically when a material is not moving but is about to move, and kinetic is when the material is moving. So these are just static numbers, but that's okay. So here is basically by 2 materials against each other. So the lower the number, obviously, the lower the friction. So you want this number low and this number low to get low friction. But let's say the normal force, let's say the weight is the same, then you want, for lower friction, you want a lower coefficient. So the lower this number is, the less friction you have. So the faster you go, the less it slows down. Friction is just being taken into. Okay, so here's a Ptfe, and you can see how low that is. So I don't know if you guys are aware of a material called Teflon, and Teflon is a very, very low friction coefficient material. Now, Teflon is used in a lot of industrial applications. Reason being is because nothing really will chemically bond to it. And we'll get into this in the rule of thumb series. But basically what friction is it's a temporary chemical bond between, or electrical bond, chemical bond, whatever, between the bottom surface of your material and the top surface of whatever it's riding on. It will temporarily attach to each other. Similar to like when you see water, if you put water on your table and the table's got like a little lip at the end, the water won't come off the table because it's being held on chemically to the table, right? Electrical bonds. So that's what Ptfe is. So let's see, what is Ptfe made out of? And Ptfes are also made from made also for 3D printers with their liners. A lot of their liners are Ptfe. It has a high melting point, and it does not have any friction. So here it is right here. It's in here in a second. It says Teflon is a registered trade name of the highly useful plastic material. Ptfe is one of a class of plastics known as polymers, blah 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 blah. Ptfe, which is basically Teflon's kind of other technical name. Many common synthetic fibers are polymers, such as polyester and nylon. So basically Ptfe is pretty much Teflon. So that is why it has such a low static friction, right? Or another thing is having tungsten carbide, which is a cutting material. It's also got pretty low static. And here's tire wet against road, rubber on road, and then wood waxed against dry snow. Again, this is like snowboard, wood waxed, right? Snowboard, a waxed snowboard against dry snow. Really, really low. What else? I don't think there's anything else that's going to be lower than Ptfe against steel or Ptfe against itself. Pretty much 0.05 to 0.02. Extremely, extremely low. So if you wanted to be able to slide your hovercraft around, you would go with a very low weight material, for example EPP, and have a skid plate on the bottom made out of Teflon. But if the material is so light, your friction will be low, and maybe the price of adding the Teflon might not even be worth it. Getting the friction to be even lower to where it will pretty much almost skid forever, as long as you have a low cross section and wind resistance has not been counted. Anyway, so this is just a quick video I wanted to go into. Obviously at this point it's not quick, but you get the idea. So I hope you guys enjoyed this video. If you like this video, please subscribe for more videos like it. And I will see you guys in my next video. If you want to support what I do, go ahead and check in the description link for my Patreon page. I'm going to be adding very soon some exclusive free content there, kind of podcast style stuff. And make sure that you keep your eye out on it for there. And also check out all my different rewards on there for my Patreon backers. Really, really cool stuff on there. I redesign every once in a while. Alright, I'll thank you guys for watching, and I'll catch you guys later. Take it easy. Peace.